Thank you. Thank you, Gabriel, for having this section and giving me a chance to share what we have learned in recent few years. And I have given this topic a few times in the talks, and in fact, many of my talks are uploaded in my YouTube channel on the topic. But today, I have the fortune of doing it in person, and it's a subject that's very large. Lots of results have been summarized in these papers, these books. But we found some new results, or in fact, new perspective that urged me to decide to actually write a book on the topic. And so more than a third of this book is going to be on fracture. And we'll see how it goes. So 4 years ago, I started to speculate, contrary to what we established, that the ideal strength of your polymer may be just as low as what you observe nominally. Secondly, the toughness of your plastics and elastomers generally have very little to do with plastic processes and energy dissipation. This runs contrary to what is established so far. So are these statements true? So to save time, a lot of the essential conclusions have been summarized in this perspective article. 7 papers have been published so far, and we use some technique that I will explain in some detail. But basically, as I said, we are fortunate to have this section, and my student is giving the 4th talk on a topic that is guided by our new understanding. So I look forward to hearing that, and I'm not going to talk about that topic, actually. My talk essentially is about the relationship between polymer physics and fracture mechanics. So I want to set the stage. When you have a polymer that's unnotched, it's generally either ductile or brittle. So if you do an extension, you'll find these 2 curves, either way. And polymer, miraculously, is capable of yielding. In other words, avoid brittle fracture. So for example, this temperature thing shows it can yield. But don't be confused. This issue of moving a few degrees, it turns brittle, we call the brittle ductile transition, is really not a subject for fracture mechanics. I want to indicate right away. So what is fracture mechanics? Fracture mechanics is needed when you realize that your nominal strength is much lower than your theoretical strength. And then you want to worry, hey, in presence of a large cut or large crack, what happened? So, as I said from the beginning, it turns out this is a conclusion that our polymers without notch is not a fracture mechanical problem. It's a polymer physics problem. To better understand the fracture in presence of a large fracture or a large crack, you want to really examine the foundation of fracture mechanics. So what is fracture mechanics? Or how do I proceed? The first thing, now you start to see, the issue is just about theoretical strength versus nominal strength. Are they comparable? Which means you want to estimate what is your theoretical strength or inherent strength. And then you want to compare with what you observe experimentally in absence of any flaws. If they are much lower than the theoretical strength, then fracture mechanics advise you that the strength of your material is weakened and determined by these 2 factors. It weakens more if you have a bigger flaws, and it's determined also by this Kc factor. In fact, the whole fracture mechanic discovered that you can take an experiment like this by making a large notch and measure the critical load at which fracture occurs, and you obtain Kc. Then you plug it back to the first formula, you have a sense of how the strength is lowered. And that's the fracture mechanics. From this, you can see the famous Griffith scaling law holds because Kc is a constant. As I said, you don't need fracture mechanics if they are comparable. Conversely, when you have a large knot, not large crack, that's where you apply fracture mechanics. So I'm going to talk about two topics. I'm very brief on the plastic part. Hopefully I have enough time to talk mostly on elastomeric systems. We have the same question. How do I know the strength, the theoretical strength, ideal strength of my polymer? I have scaling theories, but I miss two prefactors. So I cannot be certain of what is my strength. So we resort to experiment. So this is the key point, that you have a notch, you watch what will be the stress at the tip, at the point of fracture. If that stress is comparable to my nominal stress, I have one set of conclusion. Conversely, I will have another set of conclusion, right? So this is a common technique for both systems. And this is the really summary slide for anyone in a hurry to know what has happened. So we have the fortune of being a polymer scientist, that I can treat my polymer as a black box, which really offered us the fortune. In any case, we found that there was nothing new for us to discover. We were born too late, 100 years too late. All the principle is done 100 years ago. Nevertheless, what I'm about to talk about is a different perspective, unfamiliar to you. These are 5 conclusions. I want to say that I may run out of time. I only have 36 slides. So I may rush at the end because I'm going to run out of time, likely. But this is recorded, and it will be on YouTube one day. So you can pause your recording and digest what's going on here. So there are 5 essential conclusions I'm making, none of which was something very familiar to us previously. So our dear polymer offered us the chance that your crack tip is blunt, is finite, not sharp. This means your fracture does not involve just one monolayer. Thirdly, we recognize, this is discussing my perspective article, that the traditional popular approach, energy-based, lack a more insightful perspective. Fourth, all the new perspective is buried in the paper that's over 100 years old. Fifth, the framework we are familiar with in fracture mechanics generally cannot deal with the fact, in my elastomer case, my strength, my toughness is rate and temperature dependent. So let me start with very briefly, a case of plastics. We are polymer physicists, we can make a ductile polymer brittle by soaking a little bit of solvent. It turns brittle. So we want a brittle case because we want to start fracture mechanics. So you do the same thing as you learn from fracture mechanics, and then you find that you can have the tip stress resolved. In other words, the tip stress does not just grow and diverge, but start to saturate on the length scale of 50 microns, 100 microns. So I could just give you an impression of this observation. You see, I'm the one who says, don't rely on computer. It doesn't play. So let's go on to the next place, and maybe it will play there. So in any event, we were able to resolve the stress at the crack tip and find that stress just grows with the far field load linearly to the point a characteristic length scale pops up. So you can, turns out, also make a polymer brittle by having your sample thick enough. This is my theory can explain it, but I don't think I have time to do the theory for you. Okay, this one plays it, that's perfect. That's meant to be, because these two movies are similar in nature. So you try to resolve the stress at the tip by looking at birefringence. Remember the technique? Yeah. So we were anxious to find out whether that stress is comparable to, is comparable to to the nominal strength. So the same feature, you find it's linear, tip is linearly changing. So here's the summary for plastics, brittle. So if you have plastics, it turns out your nominal strengths are comparable to the true strength, which we measure from the tip. And therefore, what you learned is that the fracture mechanics in presence of a large cut is dictated by how the stress build up at the tip. So how do we understand this result, that the tip stress is growing linearly with the load? So it turns out in the very little known paper, but very essential paper, hardly summarizing any textbook, is this result that perceive a rounded, in other words, the crack is never perfectly sharp. So they treated a finite sharpness, and you can plot the stress at the tip. Lo and behold, the stress will saturate because the tip is blunt. And all the results out of this model indicate your tip should grow linearly with K, the far field load. And then you carry that all the way to the point of fracture. I claim that tip stress is inherent strength, and the K become Kc, and this is just the missing length scale in the problem. And all of a sudden you find not only why Kc is constant, but what determines the magnitude of Kc. So let's review the second problem of elastomeric fracture. This is the bigger part of the picture. In other words, there is more problematic issues about stretchable elastomers. So the first thing that you find exactly 70 years ago is, which you can do conveniently by peeling because your rubber is very flexible, so to speak. So you can peel. You find the faster you peel, the more resistance you find, more force there is. But more amazingly, when you go to lower temperature, same peeling rate, you have to use a lot more force. So for example, if this is done at 25 degrees, at a higher temperature, the resistance is much lower. But can't I just realize that higher temperature is equivalent to stretching slower? So you can do a shift. Look at this shift. You can just do a shift and claim that everything can be understood by the fact that your polymer relaxation depends on temperature. So indeed, over this region, the more complicated things later, over this region, you can think about superimposing it using WF shift. In fact, my dear friend Jan worked on this and showed that maybe we can correlate that with linear viscoelasticity. And subsequently, there are papers that summarizes the more complicated cases where you can make a transition. And our new theory actually guided us to think about how to depict this transition. So this is one of the publications that I have no time to talk about. Most importantly, they show such relationship between the resistance to fracture versus the rate you use to fracture at different temperatures. You can see these curves are of different shapes, so horizontal shift will not collapse them. For example, take that 70 years old data, they don't collapse. Well, nevertheless, it seems that we thought we found the way to think about it. Ignore the fact that the shift is not perfect. We're in a hurry wanting to suggest that this is all there is, that it's all just about the temperature effect is just about viscoelasticity. It's just about polymer dynamics. So let me summarize. Supposedly, fracture is about viscoelasticity. Why? Because I can do a shift and collapse my data, not perfectly, but I can. Secondly, well, this so-called viscous dissipation, of course, is higher at higher rate and a lower temperature. Therefore, it conveniently seems to describe the fact that the rate dependence and temperature dependence of my resistance to fracture goes away. That viscous dissipation will tell you. So in fact, one of the papers, 59, shows that it's just related to how viscosity increases as I go to lower temperatures. They have even added bonus that this view perhaps even can explain why my toughness, which is energy I need to pay per unit area, is much larger than surface fracture energy, because a lot of energy was consumed by dissipated processes. Very convenient. 3 elements. So I came from, in the case of plastics, I already knew there was no plasticity when it's brittle. In the rubber case, we know further. Please, it's just an elastic thing. Where is dissipation? So we want to look at this firsthand. So we take a piece of polymer and do the same thing, because it's important for us to know the strength of our polymer can be, determined or not. Well, lo and behold, it's the same thing, that your stress stop increasing as you approach the tip of the crack, such that you can claim to know the tip stress, and you find that tip stress to again grow linearly with the load to the point of fracture. So what we learned? 2 things. This stress saturation happens on 40 to 70 micron scale. We learned for sure, consistent with all the observations that Constantino and Gaebel has, that the fracture is not happening just involving one monolayer. It's a huge layer. That is where the characteristic length scale P came out. It's a huge. Therefore, the energy release is a huge, huge number because of this. I have said what I need to say. Really, the massive amount of, the high amount of toughness has nothing to do with a massive dissipation, but have to do with the fact it doesn't involve a monolayer. So, how do I conclude that way? Because we're looking from a stress viewpoint. Well, so far so good. That's when you have a cut. The other parallel universe is when you don't have cut. When you don't have cut, I think all of my colleagues will today agree with me, when your elastomers are fairly stretchable, we need not worry about flaws. They are flaw resistant or flaw tolerant. In that case, of course, that rupture of your unnotched sample is not a fracture mechanical problem. It is a polymer physics problem. In fact, contrary to what I just said, the textbook suggests that this is uncut is the same as the cut. It's the same physics because in both cases, the rate and temperature effect are similar. In other words, when I stretch slowly, I can only stretch this much. When I stretch fast, I can stretch more. When I go to lower temperature, I can stretch more, which is equivalent to stretching at a higher rate, according to our dear WF. But every polymer people here know this must be right. So here's the data, right? Again, nearly 70 years old. Stretching at 3 different rates. You just stretch more before it fractures, it ruptures. We use the word rupture to indicate there is no notch. And better yet, at the lower temperature, it's stronger. Wow, you can now see the deal. Do a horizontal shift. And so, indeed, they do the horizontal shift. You get a master curve. It's all summarized in the textbook, and it's all about viscoelasticity. Largely. One more. This is a more systematic piece of data done in 58. Stretching at higher temperature, the resistance to rupture or to rupture is lower. As you increase temperature, your rubber simply becomes stronger. But I do WF because lower temperature is equivalent to higher rate. So you get a master curve. We take the very same data and did WF shifts. There's something going on we don't understand. Basically, if you do the WF properly, this is the data, not that. And they don't give you a master curve. Of course, the whole burden is for me to explain why that happens. So notice that at different temperatures, at different rates, the temperature dependence is different according to this data. So I only have 3 slides that you should really pay attention. They all marked with a green star. This is the first one. God, relax. This is just 3 slides, it's over. Again, this is a paper 1960. Can read it? Basically, the last conclusion is most astonishing. If you read it, it says this problem of rate of bond rupture does not come from the temperature dependence. In other words, the temperature dependence of what you see is not a bond rupture problem. Not a bond rupture problem in 1960s. Why? Because the theory I omitted says so. And secondly, the shift seemed to work. Suggesting the internal clock is my relaxation time as a function of temperature, which of course grows like crazy as you lower the temperature. Second green star. So it seems reasonable that there's no reason to suspect my bond should heavily depend on how fast I'm stretching. This is a crucial statement. We don't expect our bond to become much stronger simply because I stretched more. But that's a wrong observation. The right question I would ask the but is, don't I need to exert more bond tension for the bond to break earlier on shorter time scales? In other words, are covalent bonds shorter lived under higher tension? Rephrase. Are bonds stronger on shorter timescales, period? The answer is a resounding yes. The last red star. After that, you can relax. The last red star, green star. Without question, your problem of rupture or fracture of the elastomers is about chain breaking. Why I say so? Because I plotted this way? No. We know, at least in the 60s, that's how we perceive the problem, the famous Lake Thomas model. It worries about calculating the energy release as a result of fracture. By focusing on how much energy I can store in a strand, such as any of those. Focusing on the energy. This model ignores the fact it's not just about focusing the energy, because we have the whole phenomenology that this thing is rate dependent. So it turns out they are doing it in the zero rate limit. Therefore, they can say, hey, let me worry about that. But what about the high rate limit? This model doesn't seem to describe what happens. So, we are speaking the same language. Transition has been invoked as a concept for a long, long time. In fact, at least as long as 60 years ago. The question to ask is how they live on. In other words, it's clearly not enough to worry about the energy it takes to break. We need to worry about on what time scale it breaks. So if you just look at the textbook, you will realize your covalent bonds will break. Okay, I don't know how many lives I need to live to get there. And then the Rin teaches us you can straighten the chain, but that only gives you 4 piconewtons. The bond breaks at 1,000 times larger. And then how it breaks? According to this, I would call it a celebrated result of DFT calculations, that this lifetime of the bond crashes. Look at the interesting region I labeled. It can go to 1/10 of a millisecond within this narrow range of the tension in the bond. And all that actually is analytically described by early on. In other words, this activation barrier that you have to overcome is explicitly related to how much tension. So it turns out the whole matter is the lifetime of my bond. Hey, how long can I live? How long can you live? Depending on how fast you're stretching. So this is the stretching, the time you consume as you stretch. So you can do a calculation. You can show, the lifetime crashes down, and I start to take a little more time as I stretch more and more to build tension, and they meet at one point, which is when these 2 timescales are the same, and you can get a numerical solution out of it based on a certain way to characterize the network structure. And here's what you find. You find that at the lower rate, it changes little with temperature and then become faster, become a stronger dependence on temperature as you go to faster. Isn't that what I just showed you? That's Smith's data. So I have a theory. I mean, I tend to tease. I mean, for the first time, I can be quantitative. So here are just some of the data. Let's dig a little deeper. Now I'm guided by my new theory. It's all about kinetics of bond dissociation. Bond has a life to live on, and it's just a matter of how much time you gave it to it. As you stretch more, tension becomes larger, the lifetime shortens, and eventually you fail. So, lo and behold, for example, at a lower temperature, you can stretch more. This is uncut, without notch. So this is sort of repeating, confirming what is known. But let me use WF. Let me match it. Sorry. Basically, you can do this, and you can even do a shift. It looks even wonderfully okay, WF. But is it true? So let me match the WF. In other words, at lower temperature, I'm going to stretch slower. At higher temperature, I'm going to stretch faster. So if WF holds, then they should fracture at the same strength. But it doesn't. These are matched, but it doesn't. So now you can, guided by this, start to go a little deeper. You can do a step strand with a pre-notch, and you step it to the same level, and then you take it to your chamber to different temperatures. You watch how fast the crack will propagate at each temperature. And you calculate the speed of it. And if you take a ratio of that speed to a reference, that's this line. That's the blue data. And WF is the red. Nothing. WF cannot capture it. Well, we know, but we should show that, right? Because the internal time scale is the bond lifetime, not the polymer relaxation time. Both of which depend on temperature similarly. Lower the temperature, relaxation is much longer. Lower the temperature, your bond is longer lived. So you can also demonstrate that. I try to save time, so I hardly have any movies for you guys. But the beautiful movies are a way for us to indicate what happens. So this is a cut, and you basically stretch to a certain level, and then you observe how it fractures in terms of the propagation speed, and you basically find the speed grows if you stretch more, because you have more tension, therefore lifetime is shorter, therefore it moves faster, cracks faster. That's it. So you can do the same. I know I have never been on time before. Seriously. So I have all the time I need. I actually, the reason I relax is I timed myself. Indeed, I had plenty of time. Maybe I did too fast. So this is one of the very curious ones. We applied our theory and understanding to anticipate this phenomenon, which, by the way, is well known in the literature. It's a fascinating phenomenon. I know Jun Su in the back is fascinated by this. What do you do? With the nudge, you stretch it to a certain level and hold. You see the thing slowly propagate. It could wait for an hour, it could wait for 10 minutes, it could wait for 3 seconds. Oh, come on. It's already speed up 10 times. But I have the time. So it's probably not even perceptible to you, but it's moving actually, as the data here shows. Okay? And then it starts to propagate much faster. So there's a transition. Same load. It makes a transition. So I think you have to be equipped with a new set of considerations to understand why this happens. This is an ongoing project, unpublished, but it's fascinating. It really is a very convenient thing. Remember I indicated much of the old data you use peeling or tearing. So you claim the so-called crack speed. But crack speed is not a variable that's essential. So the best way is to do such an experiment called pure shear. You basically stretch to different levels and watch at different levels how the propagation speed changes with the load. And you can track all that, and basically you find the whole thing is independent of how you're doing it. It only depends on how much you have stretched. In the limit where viscoelasticity does not matter. Okay, I better stop. So in any case, it turns out I misread my clock, actually. Sorry, so I misread my clock. So it turns out this is one way of thinking classically. The cost is the speed, the effect is the energy release rate, but the way we think about is the reverse, that what drives the speed is lifetime of the bond. What drives the lifetime is how much you stretch, and which you can calculate as function, as a so-called energy release rate. So we got this cause and effect flipped. So this is just a story where somehow a deeper understanding of both fractional mechanics and solid and polymer physics is necessary to reach the right conclusion. So that's the conclusion. Thank you very much.